Okay.
6.7. The power of
Hey.
internal combustion. Oh my gosh. That was ridiculous. Okay. Power of internal combustion. We'll start that. Fuel and oxygen, ingredients for combustion. What is combustion? The word combustion is just another name for burning. So combustion is burning. If we say that something is combustible, we mean that it will burn.
Let's try.
If something is non-combustible, it will not burn. Is water combustible?
No.
No.
Mine the water, mister.
Fuels such as gasoline, oil, coal, and food are very combustible substances. An internal combustion engine is one in which fuel is burned inside the engine. The steam engine, on the other hand, is an external. Can everyone hear me?
Yes.
Gloria, can you hear me?
Yes, yeah, mister.
Giancarlos, give me a thumbs up if you can hear me. Very good. Okay, Carlos as well. All right. Monsa, you can hear me?
Yes.
All right, sounds good. Just want to make sure. The other steam engine on the hand is an external combustion engine because the fuel is burned on the outside the engine. Chemical energy, a special form of potential energy, is stored in fuels. Burning allows the chemical energy to be released. Some of the released energy takes the form of light energy, which we see as flame. But most of the energy stored in the fuel is changed into heat energy. If you have ever stood next to a bonfire, you have felt the heat energy released by you have felt the heat energy released by the wood fuel. So heat energy is like the heat that you feel from a fire. That is heat energy. In the steam engine, for example, heat energy can be transferred to other objects as kinetic energy to do work. If the steam engine, for example, the heat energy released by the burning fuel is changed to water or steam, and the steam moves the piston. All right, fuel must have oxygen in order to burn. For example, have you ever taken a candle and covered it?
Yes.
Does it go out?
No.
No.
The fire or the
Fire goes out. Watch. Let's see.
Mister the fire or the how called it?
Yeah, the fire goes out because it doesn't have oxygen. All right. The needed oxygen is taken from the air. Burning fuels require a good supply of fresh air because they use up oxygen very quickly. When a fuel burns, it combines chemicals with oxygen to form hot expanding gases. The hot gases from the burning fuel heat up the cooler gases in the surrounding air, and these cooler gases are expanded greatly. An internal combustion engine is a device that harnesses the power of the expanding gases produced by burning fuel. In an internal combustion engine, a mist of liquid fuel is mixed with air and ignited inside a cylinder. The oxygen in the air allows the fuel to burn. All right. So oxygen in the air allows the fuel to burn. I think you guys are going to be doing this experiment that's on 169.
9, 10.
Come on, you're going to play with fire. Of course you're going to want to do that experiment.
Where because I don't have that thing.
There is nothing that fire in my house. You're going to be your fault.
Yeah, what's a candle? It's just a candle. It's nothing big. Okay. All right.
Yeah,
gasoline engine. Let's move on to gasoline engine.
Okay.
Gasoline is. Most automobiles are powered by an internal combustion engine that burns gasoline as its fuel. Gasoline is a mixture of hydrocarbons, which are chemical compounds derived or coming from petroleum or crude oil by refining. Besides hydrocarbons, other chemicals are also added to boost the fuel's performance. Gasolines are graded by their ability not to explode too soon or too suddenly while being compressed within the cylinders of a gasoline engine. Such explosions waste energy, may damage the engine, and cause an annoying knocking or pinging sound. This is very bad for the engine. This ability to resist knocking and to burn smoothly is a gasoline's anti-knock quality indicated by its octane number. Have you guys ever been to the gas station with your parents?
Yes.
Do you see like those numbers that are on the side?
Where?
Like what you see in the book?
Yes.
Yeah, that's the octane number. The higher the octane number, the greater is the anti-knock quality of the gasoline. Regular gasolines have lower octane numbers than premium gasolines. So the better ones are the ones with the higher number, but they cost. All right, now we're gonna look at how an engine, for example, who wants to drive a car one day? Raise your hand.
I can drive a car, mister. No.
Well, we're gonna learn how cars work, okay? So inside a gasoline engine, let's read it. Most automobile gasoline engines have pistons that move up and down or back and forth in the cylinder and operate on a 4-stroke cycle. A stroke is a single movement of a piston, and a cycle is a series of movements a piston makes each time the gasoline air mixture is burned inside the cylinder. The first stroke is the intake stroke. The piston moves down and draws gasoline air mixture from the carburetor or fuel injector into the cylinder. In the compressed stroke, the piston moves up the cylinder and compresses the gasoline air mixture. At the bottom of the compression stroke, the spark plug ignites the compression mixture, and the burning expanded gas pushes the piston down for the power stroke. In the fourth and final step, the exhaust stroke, the piston moves up, pushing the burned gas out of the cylinder. As the gasoline air mixture burns, energy is released that moves the pistons and transfers power to the crankshaft. In an automobile, the crankshaft's rotary, or the spinning, motion is transferred through the drivetrain to the car's wheels and the vehicle moves. Beside the gasoline engine and the drivetrain, other important components of the internal combustion engine are its cooling system and its lubrication system. Okay, that was a lot of big words. Let me explain it to you very small, okay? Very easy. Let's look at this picture right here, all right? So as it moves down in the first picture, this is the crankshaft, all right? It moves down and it sucks gas into this little cylinder, okay? So it has gas and air because remember, it needs air to burn. And once it has that, it'll push it up, okay, compressing it, making it small and tight. And then a spark plug will set it on fire, so it blows up. So what it'll do, it'll get super tiny, then it'll set it up and blow up. And so it pushes that cylinder down again. You see it pushed it down. And then because it's like a bicycle wheel. When you turn the pedal one time, does it come back up?
I understand.
You understand?
Yes.
You know, with your bicycle, when you turn the pedal one time, it'll come back up by itself. So that's what that is. When you push really hard on the pedal, it's going to come up by itself. And the harder you push, the quicker it's going to come up. It's the same thing with that explosion. That explosion is pushing that cylinder down, but it's on a circle. So it's going to come back up and push out all the gas that it just burned. And then it's going to come back down, suck in more gas. And it's going to push it back up to compress it. The spark plug is going to set it on fire. So it's going to blow up, push back down, and then push back up to push out all the gas that it just burned. So that's how it moves. And so normally cars have 6 or 8 of these. And so that's what gets the car to move. That's what an engine does. Kind of hard to understand, but that's how it is. Do you guys understand?
Yes.
Yeah?
Yes.
Makes sense? Okay. Now we're going to talk about cooling and lubricating system. The cooling system uses water and air to keep the engine from overheating as the engine operates and fuel burns in the cylinders. The lubrication system keeps rapidly moving metal parts in the engine from becoming too hot or wearing away as a result of friction. A coating of oil covers the metal parts and makes them slippery. The slippery oil reduces the friction between surfaces as the parts rub against each other. Now we're going to talk about the diesel engine, okay? Diesel is different than gas. The importance of diesel engines. A second type of internal combustion engine is the diesel engine. Because of its greater efficiency, the diesel engine is preferred to the gasoline engine for performing heavy-duty work. Earth movers, tractors, road graders, bulldozers, power shovels, a lot of things they use for construction. Semi-trailer trucks, many ships, railroad locomotives, cross-country buses. These and large vehicles and heavy machinery are equipped with diesel engines. Diesel engines are also used in some automobiles and in electric power plants in smaller cities. Let's look inside a diesel engine. Unlike a gasoline engine, a diesel engine produces no spark and has no spark plugs to ignite the fuel air mixture in its cylinder. So remember with the gasoline engine, the spark plug sets a little spark of fire, which makes it blow up. Diesel does not have that. Instead, the diesel engine relies upon the principle that when air confined in a cylinder is suddenly compressed, its temperature rises. The rise in temperature to about 900 degrees Fahrenheit is hot enough to ignite the fuel that is injected into the cylinder. The diesel fuel explodes violently, creating temperatures as high as 4,500 and pressures as much as 1,500 pounds per square inch as expanding gas pushes the cylinder down in a stroke. All right, so it's the same thing. That cylinder that moves up and down is getting pushed and stuff, but instead of a spark plug, just when it gets too compact, it's too hot and explodes, okay? All right, let's move on to page 6.8. Let me have Monse. You read for me.
Okay. The power of jet propulsion, power for flight. In 1903, two Americans, the brothers Wilbur and Orville Wright, flew the first power airplane. Its power source was an internal combustion gasoline engine, very similar in design to the piston engine in a car. The engine turned a propeller or prop that put the airplane through the air. Like the Wright airplane, all aircraft until about 1940 flew by means of a propeller attached to a piston engine. Jet engines were first developed in both Britain and Germany during the 1930s, and the few planes fitted with jet engines saw action in World War II. In the second partial, Mr.
Yep, keep going.
1939 and 1945. Since 1945, jet engines have been used including in military and commercial aircraft. Jet engines allow airplanes to fly much faster and higher than they could if they were powered by a piston engine and prop. How jet engines work to turbine. Most jet engines are called gas turbines because their operation depends upon a rotating turbine inside the engine. The simplest gas turbine engine is called the turbojet. Air is sucked into the turbo in the front of the engine. Then it passes through a series of rapidly spinning hydraulic blades. The blades compact the air so that it is 20 to 30 times more than the air inside the engine. Next, the compact air flows into the combustion chamber, where fuel is sprayed in and burned. The burning causes the rapid expansion of the compressed gases. The white hot gases rotate a turbine which spins. The fan blades on the front of the engine. After passing through the turbine, the gases rush with great force out the nozzle at the rear of the engine. The backward push of these not gases through the engine forward in the same way that is escaping. Escaping from a balloon causes it to flow through the air. A skid of octopus uses the same kind of jet action when it propels itself through the water by shooting out of the tube called the siphon.
Siphon.
The water flows. What is it?
The siphon.
The siphon. The water shoots in one direction, pushing the octopus or skidding in the opposite direction. I keep reading, mister.
Now we're gonna stop there. Okay, so that's how a jet engine works. Okay, so all the hot gas pushes it forward. All right, and now we're gonna go on to the next page. Let me have
Ay,
Carlos go for it, bud.
okay. Where we was?
173.
Okay. Sometimes the nozzle of a turbojet engine is extended by adding a afterburner to it. More fuel is burned in the afterburner, producing more heating and expansion of the gases and giving a great deal of extra forward power. The turbofan, a turbojet with a large fan added at the very front of the engine is called a turbofan. Some of the air passes through the fan and into the engine, but the rest of the air passes around the engine unheated. The greater amount of airflow through and around the engine gives greater forward thrust. Turbofans are used in most modern jet aircraft. The turbo the turboprop. A turboprop uses a jet engine to power and propeller. It also works much like the turbojet, except that its turbine is connected to gears which turn the propeller. Hot gases escaping from the rear of the engine give extra forward push. Turboprops are used to propel smaller commercial airplanes. The ramjet,
All right,
a
let's stop right there.
special,
So
okay.
we have the that first one that we read over here, which is the turbojet. Then we have the turbofan, and now the turboprop. Now we're gonna learn about the ramjet. Okay, go for it.
Okay. A special type of jet engine, a ramjet, is designed to function at very high speeds because it has no turbine to compress air. The air entering the engine, a ramjet must be moving rapidly through the air before it can operate. Another engine must be used to build up speed so that the ramjet can get started. The engine is called the ramjet because air rushing into the engine compressed by being forced or rammed through a narrow opening before mixing with the fuel. Ramjets work best in the missiles.
Very good. All right. This one's a very easy one. It's just talking about the types of jet like engines when it comes to airplanes, all right? So let's move on to 6.9, 175. Gloria, I want you to read for me.
The power of the rocket engine. If you have ever been to a fireworks show, you have seen rockets in action. Rockets come in a many different sizes for many different purposes, whether it be the small skyrockets that burn in the air on the 4th of July of the House Saturn V rocket used to carry men to the moon.
One sec, Gloria. You're doing very good, but we have some other people in the class who are not reading, who are looking at the camera, or who have turned off their camera, and that needs to be fixed right now. Otherwise, I will kick you out of the class and send a message to your parent for not participating.
I didn't was doing nothing of those things.
But you are fine. Hello, Mar. Hey, Gloria, you may continue reading. Thank you so much for reading.
Rockets and oxygen. Steam, piston, and jet engines all use oxygen from the air to burn their fuel. In the steam engine, fuel is burned in the air outside the engine. In the gasoline and diesel engines, the fuel is mixed with air in the carburetor and then injected in the cylinder. In the jet engine, fuel burns after it combines with the air rushing through the combustion chamber. All of these engines depend on the air for their supply of oxygen. If you were to try placing them underwater, for instance, they could not operate. Rocket engines also need oxygen in order to burn their fuel, but they do not get their oxygen from the air. Instead, they carry their own supply with them. Because they do not need air, they can run in place where air does not exist underwater or in outer space.
All right, so rockets can go underwater, so they have their own supply of air. Whereas in like the other engines and stuff like that, they need air. This one has its own supply. All right, who's gonna read next? Peña, go for it.
Rockets made in China. Rockets have been used ever since the early 1200 when the Chinese shot off their first fire arrows propelled by gunpowder. Other nations learned about the Chinese invasion by having rockets fired at them in battle. Soon rockets spread all over the world. Men worked hard over the next few centuries to improve rockets by making them lighter and giving them the ability to fly longer distances during the 1800s. Armies used rockets because they were much more frightening and dangerous than cannons. Do you remember the rocket Red Glare? Francis Scott, he wrote about it, the Star-Spangled Banner. But these early war rockets have one big drawback. They were very hard to aim and had to be fired in huge numbers to do any real damage.
All right, so rockets are hard to aim. Like, the fireworks, they go like that.
Yes.
Those are hard to aim. You don't know where they're going to go. Sometimes they go like this, okay? Same thing with rockets. So they'd aim them this way, but they'd have to have hundreds going that way just to make sure that,
Yes.
they would do damage.
Imagine that it fell to a car.
Yep. All right, let's have Lizzie. Will you read for me?
Teacher, you cut the arrow, it can fall down fast.
It'll fall down fast. Go for it, Lizzie.
Modern rocketry. The first modern rockets were developed ways. Developed during the 1930s and 40s in Germany and the United States. These rockets were much larger and faster than their ancestors. They run on liquid fuel, could be guided in flight, and carry the heavy payload. The cargo that rises in the nose of the rock. Today, rocks have a great many uses. Without rocks, space exploration would be impossible. Rocket engines have life meant to the moon and place satellites into orbit. They also power the space shuttle. Guided military rockets are called missiles. Missiles can be fired from the ground, from airplanes, or from boats. Some missiles are small enough for a single soldier to carry, while others are large enough to deliver a payload of explosive to a target thousands of miles away. In peacetime, rocks as fireworks have entertained people for centuries, especially designed cars, boats, and planes are sometimes powered by rocket engines, flares, and small short-range rockets used from signal light.
Very good. So flares are rockets. So we use flares or rockets for fun and for war, for doing bad things, okay? Or we use them to get to space. That's what the spaceships use. They use rockets. All right, I'm going to keep reading from here to end it, and then we'll be done, all right? 2 types of rocket engines. Solid fuel rockets. In the process of manufacturing solid fuel for rocket engines, chemical oxidants or oxygen-rich compounds and chemical fuels are first mixed together as powders and then hardened into a solid substance called the propellant. The propellant is packed into the rocket's combustion chamber. When an ignition flame in the chamber touches the surface of the propellant, the fuel begins to burn by combining with the oxidants. Hot expanding gases from the burning chemicals push rapidly out of the nozzle at the tail end of the rocket. The nozzle's narrow opening causes the gases to escape at the highest possible speed. The escaping gases provide the thrust to propel the rocket forward. The rocket engine stops burning when all the propellant has been used up. All early rockets had solid fuel engines. The basic design of the engine has not changed since the first Chinese arrows were made. The only real difference between early and modern solid fuel engines is in the propellant. Early rockets burned gunpowder, but modern ones can burn a variety of different chemical fuels. Solid fuel engines are best suited for all small short-range rockets such as fireworks and flares, and most military rockets. The largest solid fuel rockets ever built are the 2 booster rockets that help to push the space shuttle into orbit. It takes only 2 minutes to burn up the propellant in these 150-foot tall rockets. When empty, they are dropped from a height of about 40 miles into the ocean below. Now we have liquid fuel rockets. A liquid fuel rocket also carries both oxygen and fuel as propellants, but not in solid form. Instead, oxygen gas is condensed into a liquid by chilling it to a very cold negative 297,000 Fahrenheit. Then it is stored in the oxygen tank in the rocket. Another tank in the rocket holds the fuel, such as kerosene or liquid hydrogen. Hydrogen is a gas at normal temperatures. Liquid hydrogen is the best fuel, but it must be cooled to a liquid at temperature of negative 423 degrees Fahrenheit. Colder even than liquid oxygen in order for the engine to operate. Fuel from the fuel tank and oxygen from the oxygen tank must be mixed in the combustion chamber and ignited by a spark. When burned, the fuel combines with the oxygen and together they become rapidly expanding gases. The gases rush out of the nozzle at high speeds and propel the rocket forward. Liquid fuel engines can be used only in large rockets with enough space to house the necessary fuel tanks, fuel pumps, tubing, and combustion chamber. Spacecraft use liquid fuel engines because they allow the astronauts to control the craft's speed and direction in flight. The rocket speed is changed by adjusting the amount of liquid that flows into the combustion chamber. The more fuel that burns, the faster the rocket goes. Direction is controlled by moving the engine's nozzle back and forth or by firing small directional rockets in short bursts. Unlike solid fuel engines, liquid fuel engines can be even turned off and restarted even in flight or on the ground. This capability allows the rocket to coast through the vacuum of space without wasting fuel, also to land and take off again from somewhere such as the moon. Okay, liquid rockets are way better than solid fuel rockets, okay? That's what we use now. And so that's what the spaceships use to get up. And so say if my hand was a rocket, in order to turn and stuff like that, they have smaller rockets coming out the side. So it shoots out this way, then I'll move that way. And it shoots out this way, then I'll move that way, right? And those are what the rockets are. Okay, your assignment is you have to do 6.7, 6.8, 6.9. 6.8 is super, super easy, just definitions. That's all it is, okay? So 6.7 and 6.9 chapter comprehension check, all right? And then you have to do the experiment that's on page 169. But make sure you have your parents with you. Don't do that one. Yes.
The experiment we need to do it today.
No, you can do it another day. It's not due right now.
Okay. And how many times you give us to do the experiment?
A week. Yes, Monse.
Okay.
How can we do comparison 69? How I don't understand that.
So it says, give the word that best fits each clue. Actually, these are definitions, okay? And you just have to find what's the definition for. For example, the narrow opening of a tail end. Sorry, where is this at? Oh, yeah. What is the narrow opening at the tail end of the rocket? That's the nozzle. So the nozzle is a narrow opening at the tail end of a nozzle. Okay, so those are just definitions. You're looking for the word it's describing, okay? And then you'll identify either as a solid rocket fuel engine or a liquid rocket fuel engine, okay? And then the bottom is true or false. Pretty easy, okay?
Yeah.
Okay, you guys.
Can you add